He dedicated his entire life to proving something that no one else can see. He defied kings, clergymen, traditions, and even the heavens themselves just to follow a mathematical truth that seemed impossible. Johannes Kepler was not just an astronomer. He was a tormented visionary, an understood genius, a man surrounded by personal tragedies, poverty, religious persecution, and yet capable of deciphering the secret movement of the planets. In this video, you will meet the mind that transformed the chaos of the heavens into a perfect system, that saw beauty where others saw caprice, that was able to unite science and spirituality in a single brilliant equation. Prepare yourself. This is not just a biography. It is the journey of a man who dared to discover the hidden code of the universe. The Greatest Mathematicians of All Time, Episode 23, Johannes Kepler.
Johannes Kepler is primarily remembered for discovering the 3 laws of planetary motion that bear his name, published in 1609 and 1619. He also carried out important work in optics, 1604, 1611, discovered 2 new regular polyhedra, 1619, presented the first mathematical treatment of the close packing of equal spheres, leading to an explanation of the shape of honeycomb cells, 1611, gave the first demonstration of how logarithms worked, 1624, and devised a method for finding the volumes of solids of revolution, which, in retrospect, can be seen as a contribution to the development of calculus, 1615, 1616. In addition, he calculated the most accurate astronomical tables known up to that time, whose continued precision greatly contributed to establishing the veracity of heliocentric astronomy, Rudolphine tables, Ulm, 1627. A large amount of Kepler's correspondence has survived. Many of his letters are almost equivalent to a scientific article. Scientific journals did not yet exist, and the correspondents seem to have kept them because they considered them interesting. Consequently, we know quite a bit about Kepler's life, and in fact, about his character. This is partly why Kepler has had a sort of career as a more or less fictional character.
Kepler was born in the small town of Weil der Stadt, Swabia, on December 27, 1571, and moved to nearby Leonberg with his parents in 1576. His father was a mercenary soldier, and his mother the daughter of an innkeeper. Johannes was the couple's first child. His father left home permanently when Johannes was 5 years old and is believed to have died in the war in the Netherlands. As a child, Kepler lived with his mother at his grandfather's inn. He tells us that he used to help by serving at the inn. It is imagined that the customers were sometimes intrigued by the boy's unusual ability in arithmetic. Kepler's early education was at a local school and later at a nearby seminary. Intending to be ordained, he enrolled at the University of Tübingen, then, as now, a bastion of Lutheran orthodoxy.
Throughout his life, Kepler was a deeply religious man. All of his writings contain numerous references to God, and he saw his work as fulfilling his Christian duty to understand God's works. Man being, as Kepler believed, made in the image of God, was clearly capable of understanding the universe that he had created. Furthermore, Kepler was convinced that God had created the universe according to a mathematical plan, a belief found in the works of Plato and associated with Pythagoras. As it was generally accepted at the time that mathematics provided a reliable method for arriving at truths about the world, the common notions and postulates of Euclid being considered true, we have here a strategy for understanding the universe. Since some authors have given Kepler a name for irrationality, it is worth noting that this somewhat hopeful epistemology is far removed from the mystic's conviction that things can only be understood imprecisely, based on intuitions that are not subject to reason. Kepler, in fact, repeatedly thanks God for granting him intuitions, but these are presented as rational.
At that time, it was common for all university students to attend mathematics courses. In principle, this included the 4 mathematical sciences: arithmetic, geometry, astronomy, and music. It seems, however, that the content taught varied from university to university. In Tübingen, Kepler took astronomy classes with one of the most important astronomers of the time, Michael Mestlin, 1550 to 1631. The astronomy in the curriculum was, naturally, geocentric astronomy, that is, the current version of the Ptolemaic system, in which the 7 planets, Moon, Mercury, Venus, Sun, Mars, Jupiter, and Saturn orbited the Earth, and their positions relative to the fixed stars were calculated by combining circular motions. This system was more or less in accordance with current Aristotelian notions of physics, although there were certain difficulties, such as being able to consider uniform, and therefore acceptable as obviously eternal, a circular motion that was not uniform in relation to its own center, but rather in relation to another point, called the equant. However, it seems that, in general, astronomers, who considered themselves mathematicians, were content to continue calculating the positions of the planets and leave to natural philosophers the task of worrying about whether the mathematical models corresponded to the physical mechanisms. Kepler did not adopt this stance. His first published work, 1596, proposes considering the actual trajectories of the planets, and not the circles used to construct them. In Tübingen, Kepler studied not only mathematics, but also Greek and Hebrew, both necessary for reading the scriptures in their original languages. The classes were taught in Latin. At the end of his first year, Kepler obtained top marks in all subjects except mathematics. Mestlin was probably trying to tell him that he could do better, since Kepler was in fact one of the select students whom he chose to teach more advanced astronomy, introducing them to Copernicus's new heliocentric cosmological system. It was with Mestlin that Kepler learned that the preface to On Revolutions, explaining that it was only mathematics, was not written by Copernicus. It seems that Kepler accepted almost instantly that the Copernican system was physically true. His reasons for accepting it will be discussed in relation to his first cosmological model. It seems that, even during Kepler's student days, there were indications that his religious beliefs were not entirely in accordance with Orthodox Lutheranism prevalent in Tübingen and formulated in the Confessio Augustana. Kepler's problems with this Protestant orthodoxy concerned the supposed relationship between matter and spirit, a non-material entity, in the doctrine of the Eucharist. This relates to Kepler's astronomy insofar as he apparently encountered similar intellectual difficulties in explaining how the force of the sun could affect the planets. In his writings, Kepler demonstrated frankness in expressing his opinions, which is very convenient for historians. In real life, it seems likely that a similar tendency towards openness led the Tübingen authorities to harbor well-founded doubts about his religious orthodoxy. This may explain why Mestlin persuaded Kepler to abandon his ordination plans and instead accept a position as a mathematics professor in Graz. Religious intolerance intensified in the following years. Kepler was excommunicated in 1612. This caused him much pain,
But despite his relatively high social standing at the time as imperial mathematician, he was never able to have the excommunication revoked.
Instead of the 7 planets of standard geocentric astronomy, the Copernican system had only 6, with the Moon being a celestial body hitherto unknown to astronomy, which Kepler would later call a satellite, a name he coined in 1610 to describe the moons that Galileo discovered orbiting Jupiter, literally meaning companion. Why 6 planets? Furthermore, in geocentric astronomy, there was no way to use observations to determine the relative sizes of planetary bodies. It was simply assumed that they were in contact. This seemed to require no explanation, as it perfectly fit the belief of natural philosophers that the entire system rotated due to the movement of the outermost sphere, 1, or perhaps 2, beyond the sphere of the fixed stars, those whose pattern formed the constellations, beyond the sphere of Saturn. In the Copernican system, the fact that the annual component of each planet's motion is a reflection of the Earth's annual motion allowed observations to be used to calculate the size of each planet's orbit, and it was discovered that there were enormous spaces between the planets. Why these spaces in particular?
Kepler's answer to these questions, described in his Mysterium Cosmographicum, Tübingen, 1596, seems bizarre to 20th century readers. He suggested that if a sphere were drawn to touch the interior of Saturn's orbit, and a cube were inscribed in the sphere, then the sphere inscribed in that cube would be the sphere circumscribing Jupiter's orbit. Then, if a regular tetrahedron were drawn on the sphere describing Jupiter's orbit, the inner sphere of the tetrahedron would be the sphere describing Mars's orbit, and so on, placing the regular dodecahedron between Mars and Earth, the regular icosahedron between Earth and Venus, and the regular octahedron between Venus and Mercury. This perfectly explains the number of planets. There are only 5 regular convex solids, as demonstrated in Euclid's Elements, Book 13. It also presents a convincing agreement with the orbit sizes deduced by Copernicus, with a maximum error of less than 10%, which is exceptionally good for a cosmological model, even today. Kepler did not express himself in terms of percentage errors, and his is, in fact, the first mathematical cosmological model, but it is easy to understand why he believed that observational evidence corroborated his theory. Kepler saw his cosmological theory as evidence for the Copernican theory. Before presenting his own theory, he argued in defense of the plausibility of the Copernican theory. Kepler states that its advantages over the geocentric theory lie in its greater explanatory power. For example, the Copernican theory explains why Venus and Mercury are never seen very far from the Sun. They are located between the Earth and the Sun, while the geocentric theory offers no explanation for this fact. Kepler lists 9 of these issues in the first chapter of Mysterium Cosmographicum. Kepler developed this work while teaching in Graz, but the book was published in Tübingen by Mestlin. The agreement with the values deduced from observation was not exact, and Kepler hoped that more precise observations would improve this agreement. Therefore, he sent a copy of Mysterium Cosmographicum to one of the most important observational astronomers of the time, Tycho Brahe, 1546 to 1601. Tycho, who worked in Prague, at the time the capital of the Holy Roman Empire, had already written to Mestlin seeking a mathematical assistant. Kepler, got the job.
Naturally, Tycho's priorities were not the same as Kepler's, and Kepler soon found himself working on the intractable problem of Mars' orbit. He continued to work on it after Tycho's death in 1601, and Kepler succeeded him as imperial mathematician. Conventionally, orbits were composed of circles, and few observational values were needed to determine the radii and relative positions of the circles. Tycho had made a large number of observations, and Kepler was determined to make the best possible use of them. Essentially, he had so many observations available that, once he had constructed a possible orbit, he could verify it based on additional observations until he reached a satisfactory consensus. Kepler concluded that the orbit of Mars was an ellipse with the Sun at one of its foci, a result that, when extended to all planets, is now called Kepler's first law, and that a line connecting the planet to the Sun swept out equal areas in the same times that the planet described its orbit. Kepler's second law, that is, area is used as a measure of time. After the publication of this work in Astronomia Nova, Heidelberg, 1609, Kepler calculated the orbits of the other planets, thus establishing that the two laws also applied to them. Both laws relate the planet's motion to the Sun. Kepler's Copernicanism was crucial to his reasoning and deductions. The process of calculating the orbit of Mars was extremely laborious. Nearly 1,000 sheets of arithmetic have been preserved, and Kepler himself referred to this work as "my war with Mars." However, the result was an orbit that agrees with modern results with such precision that the comparison needs to take into account the secular changes in the orbit since Kepler's time.
For Kepler's method of comparing possible orbits with observations, it was crucial to have a notion of what should be accepted as adequate agreement. Hence the first explicit use of the concept of observational error. Kepler may have been inspired, at least in part, by Tycho Brahe for this notion, who performed detailed checks of the performance of his instruments. The work on Mars was essentially completed in 1605, but there were delays in the publication of the book. However, in response to concerns about the different apparent diameter of the Moon when observed directly and when observed using a camera obscura, Kepler worked on optics and presented the first correct mathematical theory of the camera obscura and the first correct explanation of the workings of the human eye, with an inverted image formed on the retina. These results were published in Ad Vitelionem Paralipomena, Quibus Astronomia Pars Optica Traditor, Frankfurt, 1604. He also wrote about the new star of 1604, now generally called Kepler's supernova, rejecting numerous explanations and noting at one point that, of course, this star could simply be a special creation. Following Galileo's use of the telescope in discovering Jupiter's moons, published in his Sidereal Messenger, Venice, 1610, to which Kepler wrote an enthusiastic reply, 1610, Kepler wrote a study on the properties of lenses, the first work of its kind on optics, in which he presented a new telescope design using two convex lenses, dioptrica, Prague, 1611. This design, in which the final image is inverted, was so successful that today it is generally known not as a Keplerian telescope, but simply as an astronomical telescope.
Kepler's years in Prague were relatively peaceful and extremely productive scientifically. In fact, even when things went wrong, he never seemed to allow external circumstances to stop him from continuing his work. Things began to worsen considerably at the end of 1611. First, his 7-year-old son died. Kepler wrote to a friend that this death was particularly difficult to bear because the child reminded him so much of himself at that age. Then Kepler's wife passed away. Next, Emperor Rudolf, whose health was failing, was forced to abdicate in favor of his brother Matthias, who, like Rudolf, was Catholic, but unlike Rudolf, did not believe in tolerance towards Protestants. Kepler had to leave Prague. Before leaving, he had his wife's body transferred to his son's tomb, and wrote an epitaph in Latin for both of them. He and his remaining children moved to Linz, present-day Austria.
Kepler appears to have married his first wife, Barbara, for love, although the marriage was arranged by a broker. His second marriage, in 1613, was a matter of practical necessity. He needed someone to take care of the children. Kepler's new wife, Susanna, had a brief experience with Kepler's character. The dedication letter of the resulting book explains that, during the wedding celebrations, he noticed that the volumes of wine barrels were estimated by means of a rod inserted diagonally through the cork hole, and began to wonder how that could work. The result was a study on the volumes of solids of revolution, Nova Stereometria Doliorum, Linz 1615, in which Kepler, drawing on the work of Archimedes, used a resolution in indivisibles. This method was later developed by Bonaventura Cavalieri and is part of the lineage of infinitesimal calculus.
Kepler's main task as imperial mathematician was to write astronomical tables based on Tycho's observations, but what he really wanted was to write the harmony of the world, planned since 1599 as a development of his Mystery of the Cosmos. This second work on cosmology, Harmonices Mundi Libri V, Linz, 1619, presents a more elaborate mathematical model than the previous one, although polyhedra are still present. The mathematics in this work includes the first systematic treatment of tessellations, a demonstration that there are only 13 convex uniform polyhedra, the Archimedean solids, and the first description of 2 non-convex regular polyhedra, all in Book 2. The harmony of the world also contains what is now known as Kepler's third law, which states that for any 2 planets, the ratio of the squares of their periods will be equal to the ratio of the cubes of the mean radii of their orbits. From the beginning, Kepler sought a rule that related the sizes of orbits to periods, but there was no gradual series of steps toward this law as there was with the other 2. In fact, although the third law plays an important role in some of the final sections of the printed version of Harmony of the World, it was only discovered when the work was already in the printing phase. Kepler made last-minute revisions. He himself recounts the story of the final success. And, if you want the exact moment, it was conceived mentally on the 8th of March of this year, 1618, but subjected to calculations in an unfortunate manner and therefore rejected as false, and finally returning on the 15th of May and adopting a new line of attack, it invaded the darkness of my mind. So strong was the support of the combination of my 17 years of work on Brahe's observations and the present study which conspired together that, at first, I believed I was dreaming and assuming my conclusion among my basic premises. But it is absolutely certain and exact that the ratio between the periods of any 2 planets is precisely the sesquiceltid ratio of their mean distances. While Kepler was working on his Harmony of the World, his mother was accused of witchcraft. He sought help from the law faculty in Tübingen. Katharina Kepler was eventually released, at least in part, as a result of technical objections stemming from the authorities' failure to follow proper legal procedures in the use of torture. The surviving documents are chilling. Nevertheless, Kepler continued to work. In the carriage, on the way to Württemberg to defend his mother, he read a work on musical theory by Vincenzo Galilei, Galileo's father, to which there are numerous references in The Harmony of the World.
Calculating tables, a common task for an astronomer, always involved complex arithmetic. Kepler was therefore delighted when, in 1616, he came across Napier's work on logarithms, published in 1614. However, Mestlin promptly warned him, first, that it was improper for a serious mathematician to rejoice in a mere calculating tool, and second, that it was unwise to rely on logarithms, since no one understood how they worked. Similar comments were made about computers in the early 1960s. Kepler's response to the second objection was to publish a demonstration of how logarithms worked, based on an impeccably respectable source, Euclid's Book 5 of the Elements. Kepler calculated 8-digit logarithm tables, which were published together with the Rudolphine tables. The astronomical tables utilized not only Tycho's observations, but also Kepler's first two laws. All astronomical tables that incorporated new observations were accurate during the first few years after publication. What was remarkable about the Rudolphine tables was that they proved accurate over decades. And as the years passed, the continued accuracy of the tables was naturally seen as an argument in favor of the correctness of Kepler's laws, and therefore the correctness of heliocentric astronomy. The fulfillment of Kepler's tedious official duties as imperial mathematician led to the realization of his greatest desire, to help establish Copernicanism.
Kepler died in Regensburg on November 15, 1630, after a brief illness. He was in the city on his way to receive a payment for the Rudolphine tables. He was buried in the local church, but it was destroyed during the 30 Years' War, and nothing remains of the tomb.
Johannes Kepler reminds us that science is not born from comfort. It is born from curiosity, courage, and the stubbornness to persevere when everything seems impossible. Each of his calculations, each observation, each sleepless night forever changed the way we understand the cosmos. If you've made it this far, it means you also carry within you that flame of seeking greater answers. So don't let this knowledge be lost. Like the video, subscribe to the channel, and share it with someone who needs to know this extraordinary story. Because, like Kepler, you can inspire someone else to look at the sky and see much more than just stars.